Now, let me tell you something remarkable. Here we are, sitting on this tiny speck of a planet, tucked away in one little corner of the cosmos, and yet astronomers have calculated, with extraordinary precision, I might add, exactly how much ordinary matter should exist throughout the entire universe. But here's the fascinating part. For well over 40 years now, roughly 40% of that matter has been nowhere to be found. And no, I'm not referring to that enigmatic dark matter or dark energy we're always hearing about. I'm talking about regular, visible matter that should be there, but simply isn't. You see, when we look at galaxy clusters, they don't appear to contain nearly as much observable mass as our theoretical models tell us they ought to have. Whole galaxies seem to have misplaced enormous quantities of the very material from which they formed. Even those vast stretches of space between galaxies, what I like to call the cosmic deserts, turn out to be considerably emptier than what our finest theories would predict. This missing matter must exist somewhere out there. The alternative? Well, that would mean every single one of our cosmological models is fundamentally incorrect. Each time we've searched, though, we've come up empty-handed. And believe me when I say we've made extraordinary efforts. We've employed our most advanced telescopes, conducted our most comprehensive surveys, deployed our most delicate detection instruments. Yet this missing mass continues to elude us. It slips right past our instruments as though it were some kind of phantom. That is, until very recently, for the very first time in human history, we may have finally discovered where all that missing mass has been concealing itself. And you won't believe this. It's been hiding in plain view all along. Scientists have now captured photographs of immense gaseous filaments extending some 23 million light-years between clusters of galaxies. Now, this is just one filament we're talking about, but the implications of finding it are absolutely profound. Could this be the first detailed photograph of what we call the cosmic web? As researchers continue their hunt for additional examples, this finding has the potential to settle whether our cosmological models are fundamentally sound. I'm Professor Douglas Whitfield, and what I want to share with you today is how astronomers have managed to glimpse this nearly invisible network that forms the very foundation of our cosmos, finally uncovering where our universe's missing visible matter has been all this time. And with that discovery, we can begin to unravel the true story of how our universe evolved. When we add up all the gas, dust, planets, stars, and galaxies, everything observable throughout the entire universe using every tool at our disposal, from infrared through visible light and all the way to gamma radiation, the total amount is absolutely staggering. We're talking about more than 100 sextillion kilograms. That's a one followed by 53 zeros, if you can imagine that. But here's what most people don't realize. This represents only a tiny fraction of the total matter scientists predict must exist. In truth, this visible ordinary matter is thought to constitute a mere 5% of the universe. The remainder, well, that's composed of things we don't fully comprehend yet. Scientists believe dark matter accounts for roughly 27%, while dark energy makes up about 68%. And despite having similar names, dark energy bears no relation whatsoever to dark matter. What these mysterious phenomena share is simply this: we cannot detect or observe them directly. Dark energy appears to be some form of invisible energy that's causing the universe's expansion to speed up over time. Dark matter, on the other hand, is a type of matter that possesses mass but remains invisible to us because it doesn't absorb, reflect, or emit light of any kind. So here's where we stand. 95% of our universe likely isn't made of visible, ordinary matter at all. And of that 5%, which technically qualifies as visible matter, what we call baryonic matter in the field, approximately 40% has been unaccounted for since the Big Bang occurred, some 13.8 billion years ago. Now I know exactly what you're thinking. How can we possibly know something is missing if we've never laid eyes on it? We certainly weren't present back when it all began. Fortunately, the early universe left us clear evidence to work with. Scientists have measured the cosmic microwave background radiation, which has allowed them to calculate with remarkable accuracy, better than a few percentage points, exactly how much baryonic and non-baryonic matter was created following the Big Bang. This gives us a very precise accounting of how many atoms ought to exist in today's universe. But just because something consists of material that's theoretically visible to us doesn't necessarily mean it's simple to observe. When astronomers tally up all the stars, gas, dust, and plasma we can detect, even with sophisticated models and simulations helping us, we only locate about 60% of what should be present. The remaining portion must exist for the physics of the early universe to make any sense, but until we can actually find it, we have no way to prove our models are accurate. Perhaps we've gotten everything completely wrong. Thankfully, scientists haven't been so quick to abandon ship. Instead, they've turned their attention toward determining where this missing mass might be lurking. And they've developed quite an intriguing hypothesis. The missing baryonic matter isn't the only mass that's missing, and perhaps they're concealing themselves together. Nearly 100 years ago, a Swiss-born astronomer by the name of Fritz Zwicky observed that galaxies in the Coma cluster were moving far too rapidly given the amount of gravitational force that their visible matter alone could generate. And, yes, that includes the missing material we've been discussing. Instead, he concluded that some other form of mass must be present, and in 1933, Zwicky coined a term for this missing substance. He called it dunkle Materie, the German phrase for dark matter. Several decades later, in the 1970s, an American astronomer named Vera Rubin had a remarkably similar experience. She was studying spiral galaxies and began to wonder how stars at the outer edges of these spiral galaxies could move so quickly without simply flying off into space. Once again, some unknown mass must have been pulling them back inward, and she reached the same conclusion as Zwicky had. There must be dark matter holding these galaxies together. This novel type of substance interacts with its ordinary baryonic counterpart through gravitational force, but it doesn't interact with the electromagnetic spectrum at all. What this means is that it doesn't absorb, reflect, or emit any form of light. This characteristic makes dark matter extraordinarily difficult to locate and seemingly impossible to observe, at least not directly. Nevertheless, it exerts influence throughout the cosmos on a galactic scale. It may even be assisting in concealing our missing baryonic matter. Since the 1980s, early observations of how galaxies are distributed have revealed a cosmic pattern. A web, if you will, like a framework spanning the universe. This skeleton-like structure has come to be known as the cosmic web. Within this cosmic web, galaxies aren't scattered randomly throughout space. Rather, they're organized into clusters that align along enormous thread-like structures we call filaments. These filaments intersect at nodes where the most massive galaxy clusters reside. Between these filaments lie vast voids, regions of space that are almost entirely empty. This entire network resembles a three-dimensional spider's web stretched across billions of light-years. The cosmic web structure is shaped primarily by dark matter through gravitational forces. The dark matter pulls ordinary matter toward it, and ordinary matter follows along. As time passes, this creates those dense regions where galaxies form, connected by those filamentary threads, with vast empty voids in between. Now here's the critical point. We've been able to observe and map the distribution of galaxy clusters along this web, not the strings connecting them, not the filaments themselves. Or have we? While most of the visible matter in our universe is bound up within galaxies, not all of it is. The dark matter in the cosmic web exerts a rather strong gravitational pull of its own. There, tied up as vast diffuse gas in those long strings or filaments, is precisely where large-scale cosmological simulations have predicted we might discover not only dark matter, but our missing visible matter as well. This low-density diffused gas is what we call the warm-hot intergalactic medium. But simulations are one thing, actually. Detecting these diffuse filaments is quite another, and this is where, historically, we haven't had much success, although that situation started to shift roughly 20 years ago. In 2005, NASA's Chandra X-ray Observatory captured images of two enormous intergalactic clouds of diffuse gas. We'd observed clouds similar to these around our own Milky Way galaxy and in other nearby galaxies, but never before had we seen them between distant galaxies. Could this be gas situated on the cosmic web? This represented some of the earliest evidence that the cosmic web was concealing our missing mass, but the light signal was far too faint to isolate it completely, so scientists couldn't be entirely certain. Then, in 2012, a combination of 18 Hubble images was utilized to infer the existence of a filament channeling matter into the galaxy cluster designated Able 2744. Scientists detected it by examining how light from background galaxies was distorted due to the gravitational effects of the filament's dark matter. But again, this wasn't a direct detection. We still couldn't claim we'd actually seen these structures. Moving ever closer to a concrete discovery, just 2 years following that, astronomers progressed beyond indirect detection and statistical evidence into the realm of direct observation. A team headed by Sebastiano Cantalupo from the University of California observed an enormous filament composed of hydrogen gas. Measuring nearly 2 million light-years across, they spotted it after it was illuminated by what amounts to a giant cosmic flashlight, a bright quasar shining upon it from 10 billion light-years away. This marked the first occasion that part of the cosmic web had been observed directly. Using that same illumination principle, in 2019, astronomers revealed entire networks of hydrogen filaments surrounding a massive protocluster, directly imaging the web on megaparsec scales. But these detections were only achievable thanks to our cosmic flashlights. To understand cosmic filaments as they typically exist in darkness, we required a new imaging technique. And in 2023, scientists achieved a breakthrough. At the WWM Keck Observatory, located in Hawaii, a team of astronomers had designed a dedicated instrument specifically to search for filaments of hydrogen. More precisely, they were looking for dim Lyman alpha emission, the spectral signature of hydrogen as it absorbs and re-emits radiation. And it performed beautifully. In fact, they've created entire three-dimensional maps of these filaments. This was merely the beginning of the discoveries. In January 2025, the picture became dramatically sharper. A team of international astronomers captured one of the most detailed direct images to date. Using the Multi-Unit Spectroscopic Explorer, abbreviated as MUSE, mounted on the Very Large Telescope at the European Southern Observatory, they imaged a pair of quasar-host galaxies with a cosmic filament approximately 3 million light-years in length, and using supercomputer models constructed from the MUSE data, researchers were able to simulate a filament that corresponds precisely to the one they observed in reality. This was truly a spectacular accomplishment, but there was one complication. These observations came from the early universe. They traced cooler hydrogen gas from billions of years in the past, not the hot, diffuse material thought to contain the majority of our universe's missing baryonic matter in the present day. Our models predict it stretches along thin filaments of the cosmic web in the local universe, but in this region the signal is far fainter and much harder to isolate from background noise. We appeared to be at an impasse. In June 2025, astronomers finally located what they'd been searching for. They succeeded in isolating and spectroscopically measuring the hot, low-density gas of an individual cosmic web filament in our local universe. This marked a breakthrough moment in our quest to locate the missing baryonic matter. A team of European researchers, led by principal author Konstantinos Migas at Leiden University in the Netherlands, employed JAXA's Suzaku X-ray Space Telescope to map a single filament through faint X-ray emissions across a wide expanse of space. They subsequently used the XMM Newton telescope to identify sources of X-ray contamination. In this particular case, supermassive black holes, which had to be filtered out from the data in order to map the filament accurately. In this image you can observe what they discovered: a filament of the cosmic web connecting 4 galaxy clusters, 2 positioned at each end, with each one appearing as a white spot surrounded by color. The band of purple extending between them, resembling a honeycomb or bone marrow-like texture, represents the filament of X-ray emitting hot gas. Situated in the Shapley supercluster, a supercluster containing more than 8,000 galaxies, the filament extends across a distance of 23 million light-years, which equals approximately 230 Milky Way galaxies placed end to end. Its mass measures roughly 10 times that of our entire Milky Way galaxy, and the temperature of this filament's hot gas reaches a scorching 10 million degrees Celsius. It reveals in unprecedented detail how galaxy clusters are connected across colossal distances and unveils the vast cosmic web that underpins the structure of our entire universe. Like the very bones of a cosmic skeleton upon which everything else takes form. And according to the paper's co-author, the filament corresponds exactly to what we anticipated from the best large-scale cosmological simulations of the universe. We got it correct. The latest breakthroughs in observing filaments provide crucial evidence and support for our current standard model of cosmic evolution, which we call the lambda cold dark matter model. This model is founded upon dark matter, which has proven too complex for us to observe directly thus far, so observing this once thought missing visible matter on the cosmic web represents a significant step in the right direction. But to truly determine whether our models match reality, we need more than just one or two filaments. We need to map the entire skeleton, or at least a considerably larger portion of it. And that's precisely where another mission, Euclid, enters the picture. Launched in 2023, ESA's Euclid mission is designed to assemble a more accurate picture of the cosmic web's structure and history, and to investigate the nature of dark matter and dark energy more thoroughly. Euclid will help us measure galactic shapes with exceptional precision, revealing how dark matter warps space through gravitational lensing, and measure redshifts, providing us with three-dimensional positions for each galaxy. This combination will enable Euclid to infer the locations of the dark matter filaments themselves, not merely the galaxies situated on them, and this will give us precise locations to search for additional gas. By 2030, Euclid will likely be positioned to confirm whether the cosmic web matches the results from the XMM Newton filament discovery and the pattern observed in the cosmic microwave background. If it's a perfect match, that would constitute one of the strongest confirmations of the Big Bang model in the entire history of science. If not, then something is fundamentally absent from our standard model, whether it's our understanding of dark matter, gravity, or the early universe itself. Either way, with the assistance of Euclid and these latest observations of cosmic filaments, cosmology is poised to be transformed forever. What an extraordinary time to be studying the universe.